I'm starting. Hello everyone. Today I am going to talk about asymmetric switching behavior in perpendicularly magnetized spin-wave nanopillars due to the polarizer dipole field for this week's Spin Journal Club. This paper was published at 2012 by these authors, and it reports the free layer switching field distributions of a spin-wave nanopillars with perpendicular magnetization. I want to start with spin-wave nanopillar structure. The spin-wave nanopillar structure, which is in use in this experiment, consists of magnetic multilayer films with strong uniaxial anisotropy perpendicular to the plane. Free layer is cobalt nickel and polarizer is cobalt nickel and cobalt platinum with a sufficiently higher coercivity to be considered as fixed for all measurements. And the magnetization direction of free layer can change between up and down direction, and the magnetization direction of polarizer is in down direction. So what is spin valve for? Spin valve is a device consisting of two or more magnetic conducting material whose electrical resistance can change between two values depending on the relative magnetization direction of layers. For this structure, when we apply a magnetic field perpendicular to the plane, we observe a step change in electrical resistance. The change in electrical resistance is a result of giant magnetoresistive effect. This effect, observed as a significant change in electrical resistance depending on the relative magnetization direction of layers. And the physical explanation behind it is that the spins of electrons in the current that pass through the polarizer will be aligned with the magnetization direction of polarizer. And if the magnetization direction of the layer is in parallel alignment with polarizer, the current will pass through it more easily than the magnetization of the layer is in anti-parallel alignment with polarizer. GMR effects explains why there is a change in electrical resistance, but someone can ask why there is a step change rather than a gradual change. The reason of magnetization reversal takes place without being oriented non-perpendicular angle is that the structure has uniaxial anisotropy perpendicular to the plane, and we apply the magnetic field perpendicular to the plane, which means that it is in the direction of z-axis. Another observation is that there is an asymmetric switching field behavior. Generally, the interactions between layers are described by a single dipole field. And this consideration is sufficient to understand the center shift of the center of the hysteresis loop. For this structure, the average dipolar field is equal to 20 millitesla. And as you can see from the figure, the shift of the center of the hysteresis loop is approximately equal to 20 Tesla. However, the field from polarizer can change by more than 100% from edges to center. Therefore, the inhomogeneous dipolar field from polarizer can play a larger role than can be described by a single dipole field. So to investigate the effect of inhomogeneous dipolar field, we should address it through the study of statistic of magnetization reversal process. After understanding the structure, we can continue with switching field distributions. I will use AP and P to refer to antiparallel and parallel states. Switching field distributions were obtained by ramping the applied field many times and recording the total field at which magnetization reversal takes place. These are the survival functions for distributions plotted against the total field, which is equal to applied magnetic field minus average dipole field. Survival function gives the portion that will survive after some specified time. In our case, it gives the portion that will switch after some specified magnetic field. These measurements were repeated for different lateral geometries at room temperature. These beams have been patterned into 50 nanometer times 300 nanometer ellipses by a process of E-beam and optical lithography. Relatively 0, 1, and 2 notch pairs on each side of the long axis were removed from the ellipses. First graph is for no notch, the second graph is for single notch, and the third graph is for double notch. Because we have already subtracted the average dipole field from applied magnetic field, the expected behavior is identical switching fields for transitions from AP to P and from P to AP. However, we can figure out from the survival function that distributions for transitions from AP to P are wider than transitions from P to AP, except for the single notch case. The curves intersect at 50% probability, which is by definition of average dipole field. And magnetization reversal takes place in a wide range of magnetic field for transitions from AP to P. And the differences in wideness implies asymmetric switching behavior. In order to examine distributions more closely, we can fit them into a thermal activation model. At non-zero temperatures, there is a finite probability that magnetization reversal takes place over a field-dependent energy barrier by thermal activation. And by assuming thermal activation over a single energy barrier at fixed temperature and field, we can define escape rate as this. E0 represents the energy barrier at zero field, HC0 represents the zero temperature coercive field, and gamma 0 represents the atom frequency. By doing this, we can obtain energy barriers for all transitions. Consistent with the differences in survival functions, energy barriers are different for all transitions except for single notch. And the biggest difference is in double notch, which is more than 100%. And while there is a 50% difference in no notch, there is no difference in single notch. And this effect only depends on the relative magnetization direction of layers. Because when we reverse the magnetization direction of polarizer, the asymmetric switching behavior doesn't change. We can observe it from the data in parentheses. Data in parentheses were obtained by reversing the magnetization direction of polarizer. To finalize the discussion, we need to look at the effect of inhomogeneous dipolar field from polarizer. The first thing that we can say on this graph is dipolar field is maximum at far edges and is minimum at center edges. Inhomogeneous dipolar field from polarizer assists in nucleation at far edges for transitions from AP to P. However, for transitions from P to AP, the large field at far edges work as an opposing field and increases the energy barrier at far edges. Therefore, the magnetization reversal takes place at center edges. For the exceptional single notch case, the free layer nucleates a reversed domain at notches where the gradient of the dipolar field is minimum, and the sharp divergences in magnetization creates magnetic instabilities, which disfavors the alternative reversal pathways. As a result, we can say that inhomogeneous dipolar field from polarizer changes the nucleation sites for different transitions, and this is at the origin of symmetric breaking mechanism. If we want to talk about possible uses, we can offer that inhomogeneous fields could be used to stabilize or destabilize micromagnetic states in spin-wave nanostructures. Polarizer fields could also be designed to greatly increase energy barriers. Also, the position of lithographically defined notches can remove the asymmetry in magnetization reversal processes. Thanks for listening.